In this video, we're going to talk about finding area in a normal distribution. Also, grab your calculator. You're going to want it. First, let's talk about how to find areas in any normal distribution. So first step is to draw a normal distribution or create one using technology. And remember, a normal distribution is that lovely bell-shaped curve that is split right down the middle by our mean or little mu. And then we've got our standard deviations to the left and to the right that follow that 68, 95, 99.7 rule. Gotta love it. And then we will perform calculations. So there's a bunch of different ways that we can do that. You can use a table in the book. You can also use some technology, which is where your TI calculator will come in handy. So this is the table that I'm talking about, and it's in terms of our z-score. So you can turn your normal distribution and those numbers into a standardized one with your z-scores at the bottom so that the smack dab in the middle, that mean, will become 0, and everything to the left and the right is 1, 2, 3, etc. Standard deviations. So you have the table, but personally I prefer my graphing calculator. So before we start pushing buttons on our calculator, let's put a problem into perspective. Let's say that we want to calculate the proportion of those 7th grade students whose vocabulary scores on that test. Remember that Iowa test? They're from Gary, Indiana, yada, yada. Let's actually find the proportion of kids who took that test that scored less than a 6th grade level. So that's where they scored less than 6. And if you remember in that last video, towards the end there, we took their regular scores, so that 2.19, 3.74, etc. We found the z-scores and we mapped it to this standardized normal distribution. So that's going to come in handy. I'm going to show you 2 different ways to use your calculator. Essentially, it's the same thing. One is for the z-score, so if you're working with a mean of 0 and a standard deviation of 1, and then second, if you don't turn it into a standardized curve. All right, you got your calculator handy? Great. So if you want to find the area from a specific value on your curve, whether that's a z-score or not, and you have your mu, your mean, and your standard deviation, this little whoop, that little baby sigma, you're going to use a command called normal CDF. So where you find all the commands for this video is you go second vars, and that's going to bring up a list. Normal CDF is right on the top there for you. So when you press that, you have to enter in 4 different values. So the first one is a lower bound. So we chose -1,000. That's not going to go to -1,000. You can't score a -1,000 on that test. Fortunately, I guess. And so you pick a really low bound, something that wouldn't even be on the graph. So you pick a low bound, and then your upper bound is whatever that z-score is, if you're doing the z-score. It works the same for not z-score, but our z-score in this case is -0.54, and then you put your mean, which in this case with the z-scores is always 0, and your standard deviation comes last, which is 1. Now, keep in mind that you do have to add commas here if you're working with an older operating system, but if you have a newer operating system, especially if you have that like colored TI-84, it's just going to have a list there and you just drop in those numbers. But either way, you put them in this order, you hit enter, and this is what we get. So what does that mean? That means about 29.5-ish% of students of those 7th graders tested below that 6th grade level. So this is a new slide. Your eyeballs are not playing tricks on you. But I wanted to show you how to enter this data when you haven't standardized your score. So you're not just working with that z-score there where your mean is 0 and your standard deviation is 1. It's the same process, but I just wanted to show you what it looks like when you have not z-scores to enter in. So you still do the lower bound. You can make it really, really crazy low. We still have that x is 6 there, that upper bound that we're trying to find the area from, essentially 0 to 6, really. And then now we're entering our mean is 6.84, so that's not going to be 0. And then our standard deviation is 1.55, which goes whoop, right here. Obviously, it's a long string. Calculator's not going to show all of that. So same deal, different mean, different standard deviation, slightly different answer. Interestingly enough, I prefer to not enter in the standardized values. So that's the 0 and the 1 for the mean and the standard deviation, because the z-scores we had to round. We had to round it to negative 0.54 or whatever the value was. So this one, in my opinion, is much more precise. It's off by a little bit. Both answers are great, but I prefer this one. Less work, too. So, as we said, we can estimate that about 29% of those 7th graders scored below a 6th grade vocabulary level on this test. So buckle up. We're going to use our calculator, and we're going to go through a lot of examples in this video. So we're going back to the stop the car example, which was a couple of videos ago. So as noted in a preceding example, studies on automobile safety suggest that stopping distance follow an approximately normal distribution, which is great. Great. For one model of car traveling at 62 miles an hour, the mean stopping distance, again, is 155 feet with a standard deviation of 3 feet. So our lovely friend Danielle, she's driving one of these cars at 62 miles an hour. How handy when she spots a wreck 160 feet in front of her and needs to make an emergency stop. About what percent of cars of this model, when going 62 miles an hour, like Danielle is, would be able to make an emergency stop in less than that 160 feet? Is Danielle likely to stop safely? So, we are going to use our calculator for this, and gotta love it, right? We've got our curve here. We can say that 155 is our mean, and then our standard deviations are 3 feet apart, going to the left and the right. So we're going to use that normal CDF value. So let's figure out what our lower and upper bounds are, and then, we know what our mean and standard deviations are. So once again, I'm going to make my lower bound negative 1,000. It's not broke. Why fix it? And so our upper bound here is going to be 160. So I want to know what the area or the likelihood or proportion, whatever you want to call it, of this whole green area is going to be. So my upper bound is 160. I'm going to put those two values there. And our mean with an unstandardized curve is 155, and our standard deviation is 3. So we get a result of 0.9522, yada, yada, yada. So if I move that decimal point 2 to the right, that gives me about 95% of cars of this model would be able to make an emergency stop within 160 feet. So Danielle is likely to stop safely. Love that for Danielle. So moving on from our friend Danielle, who may or may not exist, I don't know, let's talk about an actual person that does exist. So with Danielle, we were finding the area to the left of the curve, and with our friend, let's call him our friend, professional golfer Jordan Spieth, yes, had to look up how to pronounce that name because I don't watch golf, we're going to find the area to the right with this Mr. Spieth. So professional golfer Jordan Spieth hits his driver. The distance the ball travels can be modeled by a normal distribution. Again, how fun. It's got a mean of 304 yards and a standard deviation of 8 yards. On a specific hole, Jordan would need to hit the ball at least 290 yards to have a clear second shot that avoids a large group of trees. What percent of Spieth's drives travel at least 290 yards? Is he likely to have a clear second shot? So, before we do that, we don't necessarily have the normal distribution curve, so let's draw it. What we're first going to do here is we've got our axis, we've got it labeled with distance traveled in yards, we know what the mean is, we know what the standard deviations are, so we're going to draw that out. All right, so we've got a better looking curve than others I've drawn, but still pretty shaky, apologies. So put 304 smack dab in the middle, that is our mean, and then we count out 8 3 times to the left, so 296, 288, 280, and then to the right of that, so 312, 320, 328. So that's going to cover the majority, or 99.7% of our data values there. So we're looking to see what percent of Spieth's drives travel at least 290 yards. So that's about 290, so we want to know what the area is here, which will give us our percentage or proportion of how many of his drives travel at least 290 yards. And then we can answer, is he likely to have a clear second shot? So let's do that. So I may have fibbed a little bit. We definitely have a nicer looking curve over here. It's a little shaky, so it makes me feel better. But anyway, looks way better than what I can do. Anyway, we are going to use our calculator to figure out what the area is in this shaded region. So Our numbers are not going to start with a lower bound of negative 1,000. In fact, if you already guessed, the lower bound is going to be from 290, and our upper bound, well, that's the thing that we can make 1,000 if we really are into that number. But anything that would be greater than that value would be good. So let's fill these out, put it in our calculator, and figure out how to answer these questions. So second, vars, normal CDF, lower bound is 290, right there. Upper bound, again, picking 1,000, but anything greater than 328 would be solid. And then mean and standard deviation, 304 and 8, hit enter. We get 0.9599, yada yada. Move that decimal point, boop boop, 2 to the right. We get 95.99. We can round up and say about 96%. So what percent of his drives travel at least 290 yards? About 96% of his drives travel at least 290 yards. And is he likely to have a clear second shot? I'd say with 96%, yeah, he's likely to have a clear second shot. So we've talked about finding the area to the left and to the right of a certain value under a normal distribution curve, but what happens when you want to find the area between two different values? Well, let's see if our friend Jordan Spieth can help us with that. So we know the information about his drives with his driver, mean of 304 yards, standard deviation of 8 yards. Now, on another golf hole, he has the opportunity to drive the ball onto the green if he hits the ball between 305 and 325 yards. What percent of his drives travel a distance that falls between 305 and 325 yards? Is he likely to get the ball on the green with his drive? Now, you probably figured out, well, Alicia, the way to do this is to make 305 your lower bound and 325 your upper bound and do the same mean and standard deviation. Well, you genius, you, that's exactly what we're going to do. So let's get to it. So on our calculator, second vars, normal CDF, second in that menu. Lower bound 305, upper bound 325, mean is 304, standard deviation is 8. Enter, bada bing, bada boom. We get about 0.4459, move that decimal places 2 over, so we would say approximately 45% of Spieth's drives travel between that 305 and 325 yards. So he has a fairly good chance, a little less than a 50% chance, 50-50 shot, of getting the ball in the green, assuming he hits the ball straight. But I don't know anything about golf, so maybe one of you can educate me, or not. All right, so at this point we've found the area to the left and to the right and between two data points on our normal distribution curves using our handy dandy calculator. Let's work backwards from the area to find out information from our normal distribution curves. To help us understand that, of course, we're going back to the vocab scores of these 7th graders in Gary, Indiana. So let's say that we are working with the area of 90% of that curve, or area is 0.90. So what if we wanted to estimate the 90th percentile of this distribution? What would that score be? So just like with that normal CDF command, I'm going to show you 2 different ways to do this on your calculator. One with the standardized normal distribution, that's with the z-scores, and then second I'll show you without the z-scores, so not standardized. So here's what you do. Second, vars, just like normal CDF, but you're going to page down a little bit further on that list and go for inverse norm. So that's inv norm, or invite norm, I don't know, whatever you want to do. So here are the commands, and it's going to be the same for the z-scores, standardized or unstandardized, which is the normal information. So first thing that you put there is the area as a decimal. So if you're looking for 90th percentile, you are looking for an area that is 0.9 of the total area. You won't go over 1 because that's insane. That's more than 100%. You can't do that. So we would put 0.90, comma, 0, which is our mean, right? Obviously we're in z-score land, so it's 0. And then our standard deviation is up next. Now, again, depending on your operating system, you may have to enter all these things in, and you would have to type in left there, but most of your calculators will not need that left bit there, so you don't necessarily have to enter it. You can just fill out your list, hit enter, and it'll give you our little handy dandy answer here. And so in z-score land, the score, in terms of a z-score, that's at 90th percentile is 1.28. And so again, different screen, not z-score, so this is the unstandardized. Same information, second vars invite norm. I will never not see that as that, I guess. So again, 90th percentile, 0.90. And then our mean here, without the z-scores, is 6.84. Our standard deviation is 1.55. Again, you may not need that left. When you hit enter, you're going to get a different value because it's not in terms of a z-score. It's in terms of these numbers down here on your axis. So we would say the 90th percentile is at about 8.8264, which in terms of what this data is saying is that students at the 90th percentile are scoring at almost a ninth grade reading level in 7th grade, which is pretty dope. Good for you. One last example to work through. Just hang in there with me. We'll be done real soon. So this example has nothing to do with vocabulary tests or golf drives or driving in a real car. This has to do with how tall 3-year-old girls are. And to be honest with you, I don't have any idea because I don't hang out with 3-year-olds on purpose. So the problem says, according to the CDC growth charts, the heights of 3-year-old females are approximately normally distributed with a mean of 94.5 centimeters and a standard deviation of 4 centimeters. 75% of 3-year-old girls are taller than what height? So from here, we have the area. We know that 75% of 3-year-old girls, which is this area of this curve, are taller than some height. So we're going to be working backwards. We're going to be using that inv norm command, that invite norm, to figure out what that x value is. Because, right, we have the area. So let's think this through. If we think back to the example that we used in our last slide, we actually found or had the area to the left of the value. So this problem deals with the area to the right, but we can easily, take this as 100%, subtract that 75%. So we're still solving for x, but the area to the left is going to be 0.25 instead of 0.75. So we'll use that inv norm command, put in 0.25 for the area, the mean's 94.5, and then the standard deviation is going to be 4. So when we input that data, right, second vars invite norm, inverse norm, 0.25, which is the area because it's to the left of that value x, 94.5 is the mean, 4 is the standard deviation, and then we get an answer of 91.8. So that is that x value there. So we can say that about 75% of 3-year-old females are taller than 91.8 centimeters, which is that value that we solved for. All right, y'all, this is going to do it for this video. Thanks for watching.